So we'll have a 5-minute talk for the last kind of long talk in this session, and then we're going to conclude with a bunch, I think it's 8 total 1-minute spotlight videos. So I'll give Amy a minute to get set up.
Yep.
Great. So we're going to have Amy Wu give a presentation now, and she's currently at EPFL.
Okay, thank you. So I'm going to give a talk on behalf of Salman, who couldn't make it today. So I apologize if you have any detailed questions. I won't be able to answer them, but feel free to email him or get his contact information from me later. So this talk is about walking framework with his model, the 3LP model, which I mentioned earlier in my talk, and control. So this is the 3LP model. So it's an extension of the linear inverted pendulum model, but now it accounts for swing dynamics. So swing dynamics in this model is very important, as well as torso balancing. And one of the main motivations is if you look at the percentage of leg weights for humans or for Atlas, but for Coleman it's quite high. So this is the robot he uses. So swing dynamics becomes very important into the type of control that he wants to do for his walking robot. And so this is his model to be able to model that. So it's called 3LP because it has 3 linear inverted pendulums that he uses to walk. And so he has this time projection control. And so what it does is when there is a perturbation, for example, you can sense it through swing leg dynamics or center mass displacement. At that event that the perturbation happens, he looks back to the event before, like for example, heel strike, and he figures out what he should do to correct for that perturbation. So he doesn't have to wait for the next footstep in order to correct for that disturbance. He can continuously modify it, intermittent pushes during the swing or during the step in order to counter that. And so this also has closed form solutions, and there's also a lookup table with foot adjustment rules. So here's a couple of videos just to show that this type of control works. So he's moving the robot, and he's giving it some pushes, some perturbations forward, and it's able to stabilize. Without this controller, it would just fall over. And here he's got some more perturbations here, so it can recover from these pushes. And then for walking, sit walking forward, so it walks very nicely forward with his controller. And you can also lead it by the hand, so it's kind of a continuous perturbation of leading by the hand to guide it. And here's a video, this last video here is to show the robot's not quite perfect. There's a bit of backlash and some annoyances in the structure, but still his controller is able to handle all of that. So what he wanted to do was, if you notice, the 3LP model is simply inverted pendulum legs that can extend or retract, and he wanted to do something more human-like. And so what he did was convert this inverted pendulum model into something more human-like with a knee joint, for example. So this is a video of this graphic interface that he designed. And so in this graphic interface, now you go with a more human-like behavior. You can take wider steps. So by having sliders here, you can take longer steps. You can change the perspective of your animation. Let's see what else you can do. Increase step frequency. And then, yeah, there's all sorts of parameters, as you can see here, that you can modify. And so he wanted me to really encourage you guys to go to this website and to download it and check it out. And we're also in the process of trying to validate with human experiments, but it's pretty cool that you can just adjust parameters and the model or adapt. You can also do slopes, going up slopes, down slopes, and even giving it pushes in all sorts of directions. And so what you can do with this type of model is you can also perhaps estimate energetic costs. So you can take swing dynamics and torso balance from his model, and then perhaps combine it with some of the geometric changes from perhaps having to redirect your center of mass or clear the ground or to bear weight. And you can use that to try to estimate energetic costs from these mechanical components. So to conclude, he's once stressed that swing dynamics is a very important thing to model, and so it's one of the things he did in his 3LP model to try to account for these, which are a very important part of walking and robot control. He formulated simple foot stepping laws where you can adjust for perturbations continuously partway through your step instead of waiting until the end of that step. And then we're trying to link it back into biomechanics, so looking at robots and what he applies for Coleman robot and how does that fare with how humans would behave. And then, yeah, he uses this to make human-like motions, and he's going to try to do this for faster walking with robots. So that's pretty much his talk. Thank you.
Thanks, Amy, for delivering that very well. And as Amy said, if you have questions, we have 5 minutes where you can ask Amy questions. But if you have a burning email for Salman as well, you can just send him an email right now. And I'm sure he's up watching the live stream.
He is.
So, yeah. So any questions? Yep. We'll get the microphone back.
Hey, yeah, so it looked really good. One of the questions that I had, it looked like to pick the foot up, it was almost as if the whole robot was leaning as opposed to using its knee. Do you have any insight as to why that may have been happening? Because it doesn't seem to match the diagram of the simulation that he has going.
You mean this picture, or you mean
on the actual robot, the videos of Human walking, it was more leaning from side to side to pick the foot up, it seemed like, than actually just retracting its knee to lift the foot.
Yeah. So I think it's always hard to have this simulation model that's kind of ideal and to put that to the robot. There's certain limitations with trying to do so. So I think some of it comes out and how the behavior may be different in the actual robot than in what the model would show. So I think he's trying to think of ways to work around this, and maybe like changing some of the parameters to make it look more like the simulation.
Okay, thanks.
Questions from anybody else? So have you played with this robot, Amy, yourself?
The robot, a little bit, but I guess they're doing a lot of different things with it. So in addition to sort of doing perturbations with it, they're also doing robot-robot interaction, which is very cool.
Yep.
So I think it's nice because they link it also back to human experiments. So what they link, they do so. But the animation, I think, is with the GUI they have is very cool. So you can play things and it won't like adjust that frequency or slow down, but it doesn't really fall over, which I find a little bit suspicious. But I think that's one of the important things about sort of linking between biomechanics and robotics is that you can then validate some of the things that you have for your closed form solution for control and see how it would react with humans.
And you've done a lot of work studying how people move or balance. What would be the first experiment you would do with this robot to try and think about understanding about how humans might move or balance?
Yeah, so I think one thing that I'm interested in is looking at its lateral control. So I think with this robot, part of its main limitations is it would maybe, as you push robots, you take a side step in order to react. But it'd be interesting to also try to use the trunk to try to stabilize. So I think it might be a little bit difficult with robots. You have to have a pretty nice degree of freedom there, but I think it'd be interesting to try to test.
Yeah.
Question back here? Yep.
Not a question, but I was just writing Salman on WhatsApp for the first question. So the answer was he said the knee speed was limited.
Could we repeat the question again, just so we can remind everybody?
So the question was why doesn't the simulation match the actual robot where it kind of does side steps instead of lifting the knee quite high? So the answer was the knee speed is limited, so that's why you don't see much of a lift off from the ground like you see in the simulation. Yep.
Great. Thanks for reaching out for that. Any other questions or comments? So if not, I think we'll thank Amy again. I'd also ask that the 8 people